Welcome to Basic Power System Analysis using PSSE. In this lecture, we are going to review the basic concepts of current, voltage and power in a balanced three-phase system. So, let's start with it. So, what is a balanced three-phase system? In a balanced three-phase system, you would see that all the three phases, they have equal quantities. For instance, if we see this graph, here we can see that phase 1, phase 2 and phase 3 at different times have the same magnitude, but they are differentiating from each other at a certain angle. So the angle difference between each phase from the peak of first phase to second phase is 120 degree. So what we can say is that, let's suppose if we have a three-phase system, in this three-phase system phase 1 voltage will be equal to phase 2 voltage, but at a difference of 120 degrees. Similarly, phase 2 voltage will be equal to phase 3 voltage, but at an angle of 120 degree. So this is how we represent a balanced three-phase system. So if we have a balanced three-phase system, it means that we can represent it with the help of 3 wires or 4 wires. So how can we write the equation for the power in a balanced three-phase system? Now in this balanced three-phase system, you will see we have two kind of quantities. First, if we connect a system in the form of a delta or in the form of a Y. So let's suppose if we are connecting our system in the form of a Y, where all the three phases have a neutral point. So the voltage from first phase to the other phase, this will be known as VL, phase line to line voltages, or phase line to line current. Similarly, if we want to measure the voltage or take the voltage from phase to this neutral point, this is going to be known as VP, phase to line voltages. So for a power, in order for the power to flow in a three-phase system, power flow will be equal to 3 into V phase into I phase into cos theta, where theta is the angle between current and voltage. Here Vp means the voltage between the phase and the neutral. Similarly, Ip means voltage between the phase and the neutral. So if we convert this system into star delta, if we go for the star delta conversion, then we can say that V phase will be equal to V line divided by under root of 3. So we can convert this phase to neutral voltages into phase to phase voltages by easily dividing the phase to neutral voltages by under root 3. And in this case, phase current will be equal to line current. So in other words, if we want to represent the same equation, which is V 3 PIP into cos phi in line to line voltages or line to line system, what we can do is we can write as under root 3 into VL into IL into cos theta, where same theta is the angle between voltage and current. And similarly, at the end, the apparent power or S, this will be equal to square root of P plus square root of Q into under root. So the voltage, for the voltage, we can say that the relationship between line to ground and line to line voltages can be expressed by V line to ground is equal to V line to line divided by under root of 3. This is the same thing which I have explained before. Similarly, relationship for the volt ampere and the current, we can write that power is equal to under root 3 V line to line into I line, which will be equal to 3 V line to ground into IL, where S is in MVA, V line to line and V line to ground are in kV, and I line is in amperes. So if we got the feel of these quantities, what we can do is we can use these quantities to calculate the flow in the network or solve the equations in the network. So this comes from basic network analysis. So what we assume is that let's suppose we have two buses, bus 1 and bus 2. The voltages as bus 1 are known as V1. Similarly, the voltages as bus 2 are known as V2. The power coming out of the bus 2 is known as S2. The impedance of the line is given in the form of admittance Y, which is equal to conductance of the line plus susceptance of the line in the form of BIK. So now if we want to know the power which is flowing from bus 1 to bus 2, we can write that S of I in general for this for bus 1, what we can write is S1 will be equal to V1 minus V2, the difference between these two, into Y12, the impedance, the admittance between these two, or we can divide it by Z into V1, the voltage of this node. Similarly, for S2, it will become V2 minus V1 because now the reference becomes V2 into same the admittance of this line into voltages at S2. So the losses between the two lines will be whatever the power was flowing from here, whatever the power is reaching here. So if we subtract the two, we will get the losses in the line. So now we can generalize this equation. If you see here, this is 1. So I, 2, I, V1, Vi minus Vk. So the bus 1 minus bus 2, Yik, admittance between the two, and V of I. So in this form, what we do is we create a matrix. So how many lines? This is a simple two-bus network. If we take three buses, 4 buses, or multi thousand buses, what we just do is we create an admittance matrix considering all the lines between them in the form of a matrix, and then we solve this to perform the overall power flow analysis in a network. So that is all for today. I hope you understand the lecture. Thank you.